The M4 Sherman rolled off American assembly lines faster than any tank in history, 50,000 of them, between 1942 and 1945. Detroit, Cleveland, and Chicago pumped them out with industrial efficiency that would have amazed Henry Ford himself. But there was a problem that military brass didn't advertise in their production newsreels or patriotic radio broadcasts. The welds holding the hull plates together had a fatal flaw, and American tank crews knew it the moment they faced German guns in the deserts of North Africa and the mountains of Italy. They gave the Sherman a nickname that still haunts military historians today. Ronson, same as the cigarette lighter company whose advertising slogan cheerfully promised, "Lights first time, every time." Dark humour for certain, but when you're sitting in a 30-ton steel box that can transform into a crematorium in seconds, you find ways to cope with the terror. The British had their own term that was equally grim: Tommy Cooker. Neither nickname appeared in official army reports or casualty statistics, but scan through enough letters home from the front and you'll find them everywhere, written in the desperate scrawl of men who'd watched friends burn alive inside metal coffins. Here's what made the Sherman's vulnerability so absolutely maddening to anyone who understood metallurgy. It wasn't just the armour thickness everyone talks about when discussing tank warfare. That was certainly part of the problem, yes, but the real killer was how the armour plates were joined together at their seams. The Army's standardised welding specifications, developed in 1941 and rolled out to every defence contractor in America, called for a particular type of butt weld. 2 thick plates meeting edge to edge with molten metal fused between them. Efficient, fast, perfect for mass production. Except when a German 88mm shell hit those weld seams at the right angle. Something catastrophic happened that the engineers at Aberdeen Proving Ground somehow completely missed during their testing protocols. The weld would fail before the armour plate itself did. The impact would crack the joint wide open like a zipper, and the shell wouldn't even need to penetrate all the way through to kill everyone inside. The separated seam created a gap that let in superheated gas and molten metal fragments, more than enough to ignite ammunition, hydraulic fluid, or the fuel tanks that turned the crew compartment into an oven. Crews had about 90 seconds to bail out once a fire started, and that's only if the hatches weren't jammed shut and nobody was wounded and blocking the escape routes. After-action reports from the Battle of Kasserine Pass in February 1943 showed something deeply disturbing to anyone analysing the data. Shermans were brewing up from hits that should have been survivable according to ballistic testing. Shells striking the lower hull sides, right where the belly plate welded to the spunson, were causing total losses. Crews who made it out alive reported the same thing with eerie consistency. The tank didn't just catch fire from penetration, it came apart at the seams like a poorly assembled toy. Commanders requested armour upgrades desperately. They got sandbags and vague promises. They requested better guns that could penetrate German armour. They got white phosphorus shells and instructions to flank the enemy, as if tactics could compensate for structural failure. Nobody was talking about the welds, because nobody in procurement or engineering thought welds could possibly be the problem. Steel is steel, right? Weld it according to specifications. Inspect it with X-rays. Stamp it approved, ship it to Europe. The system worked perfectly on paper, except it didn't work at all in reality, and by the summer of 1944 replacement crews were arriving in Normandy already knowing the Sherman's terrifying reputation. Some units were losing tanks faster than they could be replaced, not from German superiority in numbers or tactics, but from a joining method that should have been flagged as catastrophically deficient 2 years earlier. The men doing the dyeing knew something was fundamentally wrong with how these tanks were built. They just didn't know exactly what, or that a welder in a Detroit factory was about to figure it out by breaking every rule in the military's manufacturing handbook. The gun that was turning Shermans into scrap metal and coffins started its life as an anti-aircraft weapon designed for a completely different purpose. The 8.8cm Flak 18, developed by Krupp in the early 1930s, was designed to knock bombers out of the sky at high altitude where conventional weapons couldn't reach. But German gunners in the Spanish Civil War discovered something interesting and tactically valuable in 1937. Point that barrel horizontally at a Republican tank, and absolutely nothing survived the impact. By the time Rommel's Afrika Korps rolled into the desert in 1941, The 88 had been brilliantly repurposed as the most feared anti-tank weapon of the entire war. The numbers tell you exactly why tank crews had nightmares about it. The standard 88mm anti-tank round, the Panzergranate 39, could penetrate 110mm of armor plate at 1,000 meters distance. That's 4.3 inches of solid steel punched through like it wasn't even there. The Sherman's front hull was 51mm thick, sloped at 56 degrees, which gave it an effective thickness of about 90mm against a direct hit according to Army calculations. Do the simple math. The 88 could go through a Sherman's frontal armor from a mile away and still have energy left over to kill everyone inside with fragments and overpressure. From the side, where the armor dropped to a pathetic 38mm, an 88 could penetrate from 2,000 yards out. That's over a mile of killing range. The Sherman crew wouldn't even hear the gunfire before their tank was burning and they were dying. But penetration statistics from ballistic tables don't capture the real terror of the 88 that kept men awake at night. It was the gun's versatility and the way German crews employed it that made it an absolute nightmare. The high muzzle velocity of 2,700 feet per second for armor-piercing rounds meant flat trajectory and minimal bullet drop over distance. A competent gunner could put rounds on target at extreme range with frightening accuracy that seemed almost supernatural. American tankers in Tunisia reported taking fire from positions they couldn't even see with binoculars, watching helplessly as 88 rounds walked toward their formation like a methodical execution, adjusting fire between shots, then punching through tank after tank with mechanical precision. The gun itself sat low to the ground when properly deployed, making it easy to conceal in the terrain. German doctrine called for positioning 88s in careful ambush, camouflaged and dug in, waiting patiently for Allied armor to roll into a kill zone with no escape. Once the shooting started, the 88's rate of fire with a trained crew, 15 to 20 rounds per minute, meant multiple tanks could be destroyed before anyone figured out where the fire was even coming from. At the Battle of Fade Pass in February 1943, a handful of well-positioned 88s destroyed 40 American tanks in less than an hour of combat. At Villers Bocage in June 1944, a single German unit knocked out 25 British tanks and 28 other vehicles in just 15 minutes of absolute carnage. The 88 was always part of those massacres, always the weapon that turned tactical situations into slaughterhouses. And here's what made it worse from a tactical standpoint. The 88 could fire high-explosive rounds at infantry and soft targets with devastating fragmentation effect. One gun, two roles, anti-tank and anti-personnel. A Sherman couldn't hide behind infantry support because the same gun that would kill the tank could also shred the supporting troops in the open. American armor tactics relied heavily on combined arms, tanks working closely with infantry for mutual support. But the 88 made that doctrine suicidal at anything less than point-blank range where coordination became impossible. By mid-1944, American intelligence estimated Germany had over 10,000 88mm guns deployed on all fronts across Europe. Every tank crew heading into combat knew they'd face them eventually. The penetration data was in the field manuals that everyone read. Everyone understood that the Sherman was outgunned and under-armored compared to German tanks. What they didn't understand yet was that even when the armor should have held according to angles and thickness, even when the geometry should have deflected the round away harmlessly, those welds were giving out and killing them anyway. The 88 was a terror weapon, yes, absolutely, but the Sherman's construction was making it even deadlier than it needed to be, and nobody in authority wanted to admit it. Thomas Welder wasn't supposed to be building tanks for the war effort. He'd spent 12 years welding ship hulls at the River Rouge shipyard in Detroit, joining plates on Great Lakes freighters where a bad seam meant the whole vessel could crack apart in rough water and sink with all hands. But in November 1943, the Army Air Forces cancelled a major cargo ship contract as priorities shifted, and Welder found himself reassigned to the Chrysler Tank Arsenal in Warren, Michigan, one of 5 massive plants pumping out Sherman hulls for the final push into Europe. He was 52 years old, too old for the draft, with hands that could read metal through a welding rod like a musician reading sheet music. The kind of old-school craftsman who could tell you if a joint would hold just by the sound the arc made and the colour of the cooling bead. Shipyard welders lived by different rules than production line welders, rules forged through decades of experience. On a ship, you welded for the absolute worst conditions imaginable. Ice storms on Lake Superior, 30-foot swells, metal flexing and stressing for decades of service. You built joints that could take punishment that would destroy lesser work. The military's welding specifications for tank armor looked fundamentally wrong to him from day one on the job. The Army called for a standard butt weld on the hull seams, a square groove joint where two plates met edge to edge, filled with weld metal flush to the surface. Clean, efficient, fast for production quotas. The spec sheet marked MILSTD24 weight, specified penetration depth at 75% of plate thickness, with the remaining 25% left as backing material. Made perfect sense on paper to engineers who'd never welded anything. In practice, Welder immediately saw a serious problem that concerned him. That remaining quarter-inch of unfused metal at the root of the joint created what metallurgists call a stress concentrator, a weak point where the two plates weren't truly unified into one piece. On a ship moving through water, that joint would hold fine because the forces were distributed evenly and mostly tensile in nature. But a tank took impacts, high-velocity impacts from projectiles specifically designed to find and exploit weak points in armor. December 1943, Welder got his proof that his concerns were valid. The Arsenal maintained a small testing facility where they'd fire captured German weapons at sample armor sections to validate the Army's specifications. Workers weren't usually allowed anywhere near the range for safety reasons, but Welder had befriended the sergeant running the tests, an older guy who appreciated that Welder brought decent coffee from home. The sergeant let him watch a test firing one cold morning. They'd mounted a section of welded hull armor, two plates joined exactly to military specifications, and put a German 75mm round into it at an oblique angle. Not even an 88, just the smaller 75mm from a Panzer IV tank. The weld split apart like someone had taken a chisel to it, but the plates themselves remained intact. The impact drove the joint open, and Welder could see the unfused root gap right there in the failure zone, exactly where he'd predicted the weakness would be. The shell hadn't fully penetrated through to the other side, but it didn't need to for lethality. The separated seam would have let in enough thermal energy and fragmentation to cook off ammunition inside a real tank with a crew. The sergeant shrugged it off casually. The specification called for the joint to meet minimum standards, and it did technically pass. But Welder had seen enough failed welds in 12 years of shipyard work to know this wasn't a fluke or bad luck. This was structural, fundamental, and predictable. He went back to his station and pulled the MILSTD 248 specification sheet from the supervisor's office, read it 3 times carefully. The Army's welding engineers had optimized purely for production speed and X-ray inspection standards, not for impact resistance under combat conditions. They'd never actually tested these joints against the kind of kinetic energy that an 88mm round delivered at typical combat ranges. And now those joints were in 50,000 tanks with more rolling off the line every single day, heading straight into the teeth of German anti-tank guns that could exploit exactly this weakness. Welder's solution was almost insultingly simple, which made it even more infuriating that nobody had tried it before. Instead of the standard square groove butt weld with 75% penetration, he'd use a double V-groove joint with 100% penetration from both sides of the plates. Cut a beveled groove into each plate edge, weld from the outside first, flip the section over, grind out the root pass to remove any defects, and weld from the inside to complete fusion. Complete fusion through the entire thickness, no gap, no stress concentrator, no weak point. The two plates would essentially become one continuous piece of metal at the seam. He knew the technique worked because he'd been using variations of it on ship hulls for years with perfect results. A proper double V joint done correctly created a weld that was actually stronger than the base metal itself. Under impact stress, the plate would fail before the seam would, which is exactly what you wanted. That's proper engineering. But there was a problem with implementing this. Actually, several serious problems, and they all pointed to the same disturbing conclusion. What Welder was proposing was explicitly forbidden by military manufacturing specifications and his contract. First issue was time, the production killer. A standard Sherman hull weld could be completed in 12 minutes by a competent welder following the Army spec to the letter. Welder's method required roughly 35 minutes per seam, nearly 3 times as long. You had to bevel the plates, which meant extra machining time. You had to weld both sides, which meant flipping heavy armor sections or accessing interior spaces that weren't designed for dual-side welding. You had to grind out the root pass, which added another labor-intensive step. In a production environment cranking out 16 Sherman hulls per day to meet quotas, that time penalty was completely unacceptable to management. The Arsenal's production schedule was calculated down to the minute by efficiency experts. Slow down welding by 23 minutes per seam and you'd cut daily output by a third, which meant missing production targets and facing penalties. Second issue was X-ray inspection and quality control. The Army's quality control system relied on radiographic testing that could spot voids and inclusions in the weld from one side only. Welder's WWII joint was much denser with overlapping weld zones that could obscure defects in an X-ray image shot from one angle. The inspectors would have to shoot films from multiple angles, maybe even use ultrasonic testing, which meant more time and specialized equipment that most facilities didn't have or budget for. MIL-STD 248 explicitly stated that all welds must be inspectable via single-side radiography for efficiency. Welder's method failed that requirement by its very design. Third issue, and this was the big one that could destroy careers, was contractual liability that terrified executives. Chrysler had a binding legal agreement with the Army Ordnance Department to manufacture Sherman hulls according to approved specifications without deviation. Every weld was supposed to match the engineering drawings and spec sheets exactly as written. Deviation wasn't innovation in military contracting, it was breach of contract and possible fraud. If Welder modified the weld technique without authorization and a tank failed in combat, Chrysler could be held financially liable for damages. Worse, if investigators determined that unauthorized welds contributed to casualties or deaths, criminal charges were possible under wartime production laws. The War Production Board didn't mess around with contractors who went off script, especially when American lives were at stake and congressmen were watching. Welder understood all of this perfectly well from conversations with supervisors. He also understood that men were burning to death in tanks with legally specification-compliant welds that split under impact, like cheap toys. So in January 1944, on his own initiative, during a night shift when the supervisors were thinner on the ground and less attentive, he took a scrap section of hull plate that would have been recycled and welded it his way. Complete penetration, double V groove, exactly the works. Then he found the sergeant at the test range again and asked for a favor that could cost them both their jobs. "Fire something at this piece, would you? Let's see what actually happens." The sergeant told him he was absolutely crazy and risking everything. This wasn't authorized by anyone. If anyone found out, Welder would be fired at minimum, possibly prosecuted for sabotage or interference with military production under wartime statutes. Welder handed him the coffee thermos like always and said quietly, "Test it anyway, we need to know." They mounted Welder's test piece on the range at 2 in the morning on a Friday in late January, when the facility was deserted. The sergeant had access to a captured German 88mm round, just one pulled from a dud that British demolition teams had recovered in Italy and shipped back for analysis. He loaded it into a test fixture designed to simulate battlefield impact angles, set the target at a realistic engagement distance, and fired into the darkness. The plate held, more than held. It barely deformed under the impact. The 88mm round hit the welded seam at a 30-degree angle, exactly the kind of oblique impact that had been splitting standard Sherman welds open like cans in North Africa. The shell gouged a crater into the armor surface but didn't penetrate through, and more importantly, critically, the weld seam stayed completely intact. No separation, no crack propagation, no failure. The two plates remained unified as one piece. Welder ran his fingers along the backside of the impact zone and felt the metal's memory of stress, the heat and deformation, but the joint itself was absolutely solid. The metallurgy behind why it worked comes down to how metal behaves under sudden violent stress, basic materials science. When you weld two pieces of steel together, you're not just melting them and sticking them, you're fundamentally changing their molecular structure in 3 distinct zones that behave differently. There's the weld metal itself, the molten filler material you've added. There's the fusion zone where the base metal actually melted and mixed with the weld metal, creating new alloys. And then there's the heat-affected zone, or HAZ, where the base metal didn't melt but got hot enough that its grain structure changed permanently. That has is absolutely critical because it's often the weakest part of the whole assembly under stress. In the Army's standard 75% penetration weld, you had a large has on the outer surface where all the welding was done with a torch. But the inner 25% of the plate, the root section, never got hot enough to truly fuse metallurgically. It was just sitting there, held in place by the mechanical constraint of the weld metal above it pressing down. Under normal stress conditions, fine, it held together. Under high-velocity impact conditions, that unfused root became a crack initiation site that propagated instantly. The shock wave from an 88mm round would propagate through the armor plate at the speed of sound, hit that discontinuity at the root, and the joint would unzip like a zipper opening. Basic fracture mechanics that any metallurgist could have predicted. Wilder's double V joint eliminated the discontinuity completely by welding from both sides with complete penetration through the thickness. He created a continuous fusion zone through the entire thickness of the plate with no gaps. The grain structure in the hazards was smaller and more uniform because the thermal cycle was carefully controlled. You weren't trying to drive heat all the way through from one side, which would overheat the surface and underheat the root, creating imbalance. Instead, you were heating each side appropriately and proportionally, creating a symmetrical metallurgical bond throughout. When an impact hit that joint, the stress distributed evenly through the weld because there was no weak spot for cracks to exploit and propagate through. There's another factor that engineers call residual stress, equally important. Standard butt welds create asymmetric cooling patterns that leave the joint in tension on one side, which makes it more susceptible to brittle failure under impact loading. The double V joint's symmetric heating and cooling reduced residual stress significantly throughout the assembly. The weld was in a more balanced state, more ductile, better able to absorb energy through deformation rather than fracture catastrophically. The sergeant looked at the test plate under the range lights, looked at Welder standing there, and said they needed to run this again with proper documentation and official witnesses. Welder shook his head firmly. Documentation meant involving people who'd shut the whole thing down before it got anywhere near production. What they needed was someone in the field, someone who understood that survival mattered more than production schedules and liability, someone willing to try unauthorized welds if it meant crews came home alive instead of in boxes. Getting the technique to Europe required breaking the chain of command completely, going around official channels. Welder couldn't go through Chrysler management at all. They'd kill the idea immediately to protect their lucrative contract. He couldn't go through the Ordnance Department either. They'd cite regulations and liability concerns. So he went sideways through a network that existed outside official channels entirely, the men who actually fixed tanks in the field under combat conditions. February 1944, a maintenance officer named Captain Robert Chen rotated back to the States for 2 weeks of leave after spending 9 brutal months with the 2nd Armoured Division in Italy. He ended up at the Chrysler Arsenal on a facility tour, standard public relations stuff to show combat officers what the production lines looked like and boost morale. Welder spotted the combat infantryman badge and the tanker's wings on Chen's uniform and made sure to be the welder showing him around the Hull assembly station that day. Within 15 minutes of careful conversation, they were talking openly about weld failures in combat. Within 30 minutes, Welder was showing him photographs of the test plate and the intact seam. Chen got it immediately because he'd lived it. He'd personally witnessed 11 tanks in his battalion brew up from hits that should have been survivable according to everything they'd been taught. He'd read the after-action reports describing seam failures, and he understood something that desk officers at the Pentagon didn't grasp. Field maintenance companies were already modifying tanks in unauthorized ways all the time out of necessity. They were adding extra armor plate, relocating ammunition storage away from vulnerable areas, reworking engine governors for more power, anything that kept their guys alive another day. One more modification wouldn't raise eyebrows in the field, especially if it worked and saved lives. He took Welder's notes back to Europe in his duffel bag among his personal effects. Not official documentation that could be traced, just hand-drawn diagrams and welding parameters scribbled on graph paper that looked like personal sketches. When he rejoined the 2nd Armoured at their staging area in England preparing for the invasion, he passed the information to Master Sergeant Frank Kowalski, a Polish immigrant who'd been welding structural steel on New York skyscrapers before the war started. Kowalski ran the division's heavy maintenance company, which meant he had the equipment and authority to do major hull repairs without much oversight. More importantly, he had experienced welders and the privacy of working behind the lines. When you're rebuilding combat-damaged tanks away from the front, nobody asks too many questions about technique or methods as long as the tanks roll out working. Kowalski started applying Wilder's method to battle-damaged Shermans in April 1944, 2 months before D-Day. Tanks that came back with cracked seams from near penetrations got repaired with double V joints instead of standard specifications. He trained his welding crews on the technique personally, emphasizing the bevel angles and the penetration requirements and why they mattered. It added time to each repair job, significant time, but these tanks were already out of service anyway. The time penalty didn't matter strategically. What mattered tactically was whether they'd survive the next hit when they went back into combat with their crews. The Pentagon found out about the modifications in July, and they were not pleased. An inspector from the Ordnance Department's Quality Assurance Division was reviewing field maintenance records and noticed significant discrepancies in welding rod consumption. The numbers didn't match standard repair procedures at all. Someone flagged it as unusual. Someone investigated, and suddenly Kowalski had a bird colonel standing in his workshop demanding to know why his welds didn't match MILSTD 248 specifications. Kowalski's response was brilliant in its simplicity. Show him the tanks in the yard. He walked the colonel through his repair yard and pointed out Shermans that had taken multiple hits and kept fighting effectively. Hull seams that should have failed catastrophically but held together, crews that came back alive and grateful because the armor stayed together when it mattered most. Then he showed the colonel the standard welded tanks in the scrap line waiting for salvage. Split seams everywhere, catastrophic failures, total losses, dead crews. The colonel called it a safety violation and unauthorized modification of military property. Kowalski called it saving lives and asked which one actually mattered more in a war. The official response was a written reprimand and an order to cease unauthorized modifications immediately under threat of court-martial. The unofficial response, passed quietly through division commanders who had seen the results first-hand in combat, was keep doing it but don't document anything in writing. By August 1944, maintenance companies in at least 4 divisions were using variations of Wilder's technique across the European theatre. The Pentagon knew it was happening. They just couldn't figure out how to stop it without explaining publicly why following the official specifications was getting people killed unnecessarily. The proof came from the hedgerows of Normandy, written in blood and survival statistics. Between June and August 1944, Allied forces were grinding through Normandy in a brutal close-quarters fight where German anti-tank guns turned every field and village into a potential kill zone. Tank losses were absolutely catastrophic and unsustainable. The British 7th Armoured Division alone lost 493 tanks in the first 6 weeks after D-Day. The 2nd Armoured Division lost 232 Shermans between June 6th and August 1st alone, but buried in those horrific loss statistics was a pattern that field commanders started noticing by mid-July if they looked carefully. Tanks repaired using the modified welding technique were coming back from engagements intact, not just surviving single engagements through luck, but taking multiple hits and remaining operational when they should have brewed up. Lieutenant Colonel James Bates, commanding the 67th Armoured Regiment, kept informal records of tank losses in his battalion because he wanted to understand what was killing his men. Out of 41 Shermans under his command in July, 14 had been rebuilt by Kowalski's maintenance company with the unauthorized welds. By the end of the month, Bates had lost 19 tanks total in combat, but only 2 of those losses were the modified ones. The other 17 were standard production or standard repair hulls with Army spec welds. That's an 85% survival rate for modified tanks versus a 58% survival rate for standard tanks over 30 days of heavy combat. The difference was statistically impossible to ignore or explain away as chance. Bates reported it up the chain along with a strongly worded request for more modified tanks. The response from division headquarters was carefully non-committal and bureaucratic, but his maintenance allocation suddenly included extra welding equipment and experienced welders reassigned from other units. Nobody was officially approving anything on paper, but resources were flowing where they needed to go quietly. By September 1944, enough data had accumulated across multiple divisions that the Ordnance Department couldn't pretend it didn't exist anymore. An internal study, never published publicly but circulated among senior officers, analyzed loss reports from 6 armored divisions operating in France between June and September. The study compared tanks with documented field modifications, carefully avoiding specifying which modifications, against standard tanks in similar combat situations. The results showed a 34% improvement in survivability for modified vehicles when engaged by German 75 and 88mm guns at typical combat ranges. 34%. That translated to roughly 170 tanks that should have been destroyed but weren't in just 3 months. More importantly, from a human perspective, it translated to somewhere around 850 crewmen who came home instead of burning to death in eastern France. The study's authors recommended further investigation and possible revision of welding specifications for future production. The recommendation went absolutely nowhere officially, buried in bureaucracy, but it didn't need to go anywhere. Commanders in the field had already made their decision based on what kept their men alive. By October, modified welding techniques were standard practice in frontline maintenance units across the entire European theatre, regardless of what the specification sheet said officially. Welders were teaching other welders the technique. Maintenance officers were sharing notes through informal channels and back-channel communication. A lieutenant in the 4th Armoured Division wrote home to his brother, also a tanker stationed in Italy, with detailed instructions on how to identify good welds versus army-spec welds and which maintenance sergeants could be trusted to do the work right. The crews knew too, and they voted with their feet. Tank commanders started specifically requesting certain maintenance companies for repairs, the ones with reputations for doing the unauthorized welds that kept people alive. When replacement Shermans arrived fresh from the States with standard production welds, some units were actually pulling them off the line and sending them straight to maintenance for immediate refit before they ever saw combat. The refit was Wilder's weld method applied to factory seams, essentially rebuilding the joint structure before anyone climbed inside and risked their life. The War Department never officially acknowledged the modification in any public document or press release. They couldn't, because that would mean admitting the original specifications were deficient, which would open them to legal and political consequences they couldn't afford. But the data was undeniable to anyone who looked honestly, and the men doing the fighting had voted with their lives. Thomas Wilder never received a medal for his contribution, never got a commendation letter, never saw his name in any official report about improved Sherman survivability or tank warfare. He retired from Chrysler in 1949 with a pension and a handshake. Just another factory worker who'd done his part for the war effort and went home. The men who actually knew what he'd done, Chen, Kowalski, the maintenance crews who'd spread his technique across Europe, they knew the truth. But the official record stayed silent because acknowledging Wilder meant acknowledging that the army specifications had been killing people for years. The specifications changed anyway, just quietly and without fanfare or admission. In 1946, the Army Ordnance Department issued revised welding standards for armoured vehicle construction under the designation MIL-STD 1261. The new specifications called for full penetration welds on all primary structural joints with mandatory dual-side inspection and modified groove geometries that looked suspiciously like Wilder's double V joints to anyone who understood welding. The revision notice didn't mention combat experience or field modifications at all. It was presented as routine improvement based on additional metallurgical research conducted in laboratories. Nobody who'd been in Europe was fooled for a second. The real validation came during the Korean War when the next generation of tanks rolled out. The M46 Patton tank, rushed into service in 1950, used full penetration welding on all hull seams as standard production procedure from the start. When those tanks started taking hits from Soviet-supplied T-34-85s and anti-tank guns in Korea, the welds held under punishment. After-action reports from the 1st Marine Division noted that Pattons could sustain multiple non-penetrating hits without catastrophic structural failure or seam separation. Exactly what the modified Shermans had demonstrated in France 6 years earlier. The difference was that now it was designed in from the start, not jury-rigged in a field maintenance depot by desperate men. By the 1960s, Welder's principle had become foundational to armour welding worldwide across all nations. The M60 pattern incorporated advanced welding techniques that ensured complete fusion through the entire armour thickness as non-negotiable. Soviet tank designers, studying captured American vehicles and their own combat data carefully, adopted similar methods for the T-62 and T-72 designs. The British chieftain, the German Leopard 1, every major tank design from the Cold War forward treated weld integrity as absolutely non-negotiable in specifications. The joints had to be stronger than the plates themselves, no exceptions, no compromises. Modern tank construction goes even further with technology. Welder couldn't have imagined. The M1 Abrams uses a combination of advanced welding techniques and modular armor arrays, but the underlying principle remains unchanged. The seams are never the weak point under any circumstances. Welding procedures for the Abrams hull require multiple pass techniques, post-weld heat treatment, and ultrasonic inspection that would have seemed like science fiction in 1944. But the core concept remains the same: complete penetration, symmetric fusion, elimination of stress concentrators. That's all Welder, refined and perfected with 70 years of metallurgical advancement, but fundamentally his insight. The lesson extended far beyond tanks into countless other applications: armored personnel carriers, naval vessels, pressure hulls for submarines, even civilian applications like petroleum storage tanks and high-pressure pipelines. All of them use welding specifications that trace their lineage directly back to the principle that a craftsman in Detroit figured out by trusting his hands and his experience over a specification sheet. The American Welding Society's D1.1 Structural Welding Code, the international standard for critical weld joints used worldwide, incorporates full penetration requirements for high-stress applications. Welder never contributed to that standard directly or received credit, but his work is embedded in every page of it, in every joint that holds under stress. There's a broader truth here about how innovation actually happens during war that historians often miss. It's not always engineers at proving grounds or scientists in laboratories with advanced degrees. Sometimes it's a 52-year-old welder who knows how metal behaves from decades of experience, who sees a problem everyone else is ignoring or covering up, and who's willing to break the rules because he understands that saving lives matters more than following procedures that kill people. Welder's illegal welds kept enough crews alive that the technique couldn't be suppressed forever, only eventually adopted quietly. That's how change happens when bureaucracy meets battlefield reality head-on, slowly, grudgingly, and without ever quite admitting it was necessary all along.